So this chapter is about pseudo random number generation and stream ciphers. So there are two parts in it. Basically, how do you generate a random number, and then how do you use it to encrypt? All right. In particular, we'll talk about one scheme called RC4. Pseudo random number. First of all, pseudo means half. They're not fully random. They're only half random. Okay. But so we need a random number. Say for example, nonce. We saw that we need to generate a number which is used only once, and so we can generate a random number, and so that and we don't want to use it again, so that nobody can play it again, and all these things need a random number, right? So we can use a pseudo number. Pseudo means that it is not fully random, and as you will see in a minute, when you generate a random number, you need something to begin with, a seed. If you use the same seed today and you use the same seed tomorrow, you will get the same number today and you will get the same number tomorrow. All right? And therefore, it is deterministic. There is no probabilistic here. This is deterministic, basically. And you can reproduce it, and you know the formulas. Everybody can create the whole stream. So this is not secure, but it is random. It is not secure because you know the whole thing, but it is random because you do any randomness test, it will pass the test. So statistically it is random, but for security it is not good, right? It is not secure. Here is a simple example, slide number 7-4. 7-4. You can see 7-4? Yeah. Okay, so 7-4 basically shows a very simple generator. The generator is xn is equal to 5 times xn minus 1 plus 1 mod 16. Okay, you could take any number of the previous. So in general, you could take xn minus 1, xn minus 2, xn minus 3, and make some function of it, xn a function of some previous values. A very simple example is you just take the xn minus 1, multiply it by 5 and add 1 and do mod 16. So if you start with x0 is equal to 5, that is the seed, first number you get is 5 times 5 plus 1, which is 25 plus 1, 26, mod 16 is 10. Alright, now you take 10 and you put it in the same formula, you will get 3, and so on and so forth. So basically the numbers would be 10, 3, 0, 1, 6, 15 as shown in this slide. That is what you will get for the first 32 numbers. You notice that the first 15 numbers are unique, 10, 3, 0 up to 5, and then again we see 10, 3, 0, 1, 6, which is just a repetition. So there is a cycle. Okay, so if you divide every number by 16, you will get numbers like 0.6250, 0.1875, 00, and so on and so forth. Now, if you do any statistical test on it, it will pass, or most statistical tests will pass. However, it is all deterministic. There are several things. First of all, the cycle length is very small, 16 or 15, some number like that. And so you really don't want to use this as a generator. If you were to use this, you will have mod not 16, but mod 2 raised to 16 or maybe 2 raised to 32 or something like that, large number, so that the cycle is large. And then there are ways and there are rules as to how you select the multiplier 5 and how do you select the add 1. We teach actually a great detail of this in my other course, which is performance analysis course, where you need the random numbers for simulation. And this kind of generators are good for simulation. And so next slide, 7.5. We talk about what these different things are. First, X0 is the seed, and all the random numbers are called pseudo-random because we can predict them, and they are not fully random. Then there is a cycle length. As you can see, cycle length, the sequence will go through some numbers and then come back to the same number, and then it will come back to the same number. Once it comes back to the same number, it will repeat the previous cycle. There might be a tail in some cases where you start from the seed and you go and the cycle comes back to some other value in the middle. So there's a tail length. The main important thing, and so the whole thing, the combination of tail and the cycle is called the period. So there are three values: period, tail, and cycle. You really want the cycle length to be large, and that means your mod value has to be with a large number. Generally, we use 2 raised to 31 for 32-bit machine, or 2 raised to 32 even, and for 64-bit machine, we might use 2 raised to 64, so that the cycle length is very large. And these generators are called LCG, linear congruential generator. And I will explain the meaning in a minute, but these were invented by this guy named D.H. Lehmer in 1951. And his invention was that if you take any number A and you raise it to the power n and you do mod m, then the successive numbers that you get have good randomness property. So actually xn equal to a raised to n mod m is same as saying that xn is equal to a times xn minus 1 mod m, because xn minus 1 is a raised to n minus 1. And if you multiply it by a, you get a raised to n. So this formula, instead of writing a raised to n, we write xn is equal to a times xn minus 1, the previous value of random number, mod m. M is the modulus, a is the multiplier. And this is called linear congruential because you see the function xn is equal to a times xn minus 1 is a linear function. And and this is called multiplicative Vaidev because we didn't add anything. And then people studied it quite a bit. And if you are familiar with Knuth, he wrote the whole book on art of programming, whole set of books. He has, I think, 1 or 2 volumes filled with analysis of this kind of generators. And so people have analyzed this quite a bit, and they find that it is better to use mixed generator, which is, you have a times previous number plus some other number b. And there are rules as to how you select these. Okay. So Lehmer actually, when he wrote this first thing, he said a should be 23 and m should be 10 raised to 8 plus 1. Those were his choices because he was working on ENIAC, which is a 8-bit digital machine, decimal machine, 8-digit decimal machine. So 10 raised to 8 is the biggest number that they could put in, one byte, in one, whatever, we don't want to call them byte because each digit is probably, more than 1 bit. And so so that's the number he chose, 10 raised to 8 plus 1. And 823, which is not only prime but also relatively prime to 10 raised to 8 plus 1, means they don't have any common factors. Or at least 23 is not a factor of 10 raised to 8 plus 1. And then it was generalized to this mixed thing which we wrote down, xn is equal to a times xn minus 1 plus b. And so there is some mathematics called theory of congruences. And so those people have analyzed these generators. And so we go into a little bit more detail in the performance analysis course, and this is not required here. So I will not go any more than this. I just wanted to mention this here because the book mentions it. And the main idea is that these generators, while they are good for randomness, they are not good for security because anybody can reproduce it, the whole sequence. And not only that, if you give me 2 or 3 numbers in this sequence, I can calculate A and B and M. So these are very easy to break, and so these are not used. But what we use is, now we will talk about the real random number generators which are used for security. One of them is Blum-Blum-Shub generator, BBS generator. So these are names of the people. This particular generator uses the least significant bit from this formula. You do xi is equal to xi minus 1 squared mod n. Okay, you take the previous number, square it, do mod n, and then you take the least significant bit. So you write down the bits of xi. You write down the xi, and then you take the least significant bit, which is the 0th bit, on the right side, right? Now n has to be p dot q, where p and q are prime, and p has to be such that p mod 4 is 3, and q has to be such that q mod 4 is 3. Alright, so these are the conditions that these guys have put. And again, there is a whole analysis. If you go back to the BBS paper, original paper, which we don't need to really, then they would have justified as to why this is a good generator, why these conditions have to be satisfied, because if you break the condition, then the whole properties go away. So basically, example of P would be 7. Now, if you see the 7 satisfies all the properties. First of all, 7 is a prime, and then 7 mod 4 is 3, right? Another number we could use is Q is equal to 11. 11 is a prime. 11 mod 4 is 3. So it satisfies that condition. And now you take 7 and 11 multiply, you can use n is equal to 77. Alright, obviously you will not probably use these small numbers. You will use large numbers. But this is an example. Basically, whatever number you select, P and Q, they have to be prime. And they have to be such that the P mod 4 is 3 and Q mod 4 is 3. And if you select that n like that, then you get the randomness such that you cannot predict the k plus first bit given the k bits with probability greater than half. So if suppose I gave you the previous k bits of this sequence, you cannot tell me what the next bit would be. It could be 0 with probability half, and it could be 1 with probability half. And that's what we want, remember, is that we don't want it to be predictable. And so they have shown probabilistically that if you do this, then the next bit cannot be predicted. Basically, if the next bit had a probability of, let's say, 0.6, then you would somehow bet that that bit is value. Let's say if it's 6.6 probability is 1, then you would bet on 1 and you will win, and some more often than not. But with half, you win and lose, right? Equal number of times. So security rests on the difficulty of factoring n. So the thing is, here n has to be kept secret. This is your key, and not only that, n has to be such that if somebody found it, they would not be able to factor it easily to find P and Q. Okay, and so we will see that this kind of properties are used later on in other encryption techniques that we are going to do. You need large numbers that cannot be easily factored. If somebody can factor them, then they can break it. Okay? So that's the whole thing, is that this not only passes the statistical test because it gives you half probability, but it also passes the secrecy test as long as n is secret. Okay? Now, since n is a large number, the whole operation xi square mod n is quite a bit time consuming, and so it is not used for many times. You can use it to generate random keys, but you don't use it to generate random stream, because for random stream, if you're doing random stream at 10 gigabits, you need to be able to generate 10 gigabits per second of random stream. That would be difficult to do with this kind of generator, but you can generate a 128-bit key or 56-bit key with this generator, and then use it some other techniques that we'll talk about to generate random bits at a high speed. Okay, so basically there are three kinds of generators. I mean, there are three kinds of things we are going to talk about in this chapter. First is TRNG, true random number generators. True means you cannot repeat them. They are not pseudo. Second is pseudo random number, PRNG, pseudo random number generators. And third is PRF, pseudo random functions. Alright, now true random number generators, for those you need things that do not repeat. So you might take the air temperature, you might take something which is totally random and then use that as the input to get some output. And inside a computer, you might read some voltage, which might be, and take some particular bits of the voltage number, and so that way it will be truly random. We use truly random. We use truly random numbers for encryption, but we don't use it in simulations, because in simulation the requirement is just the opposite. In simulation, we need to be able to repeat a simulation, show it to somebody else, and get the same result. And therefore, we use pseudo random numbers. The ones that we saw so far in LCG was pseudo random number, and they are good enough for simulation because they are random and they can be reproduced. Okay. And then if you get this random number generation and you combine this with some context specific values, then you get a function which is pseudo random. So an extension of random number is that you take whatever algorithm you have for pseudo random generation, and you take some values which are related to the context, so anybody else can use the same context value and get the same value output, right? So that would be pseudo random function, and we'll see the examples of these in the next few slides.